Let's look at problem 16. We have a pendulum. The range of motion is limited by this wall on the left-hand side at an angle of about half of theta zero being the full range of angular motion. Question is, how much does the time period of travel, how much is that reduced? What value is that in seconds? Right? The answer is correct. This solution is a bit involved here. There's a few points we can talk about. Let's just go through them. First off, as soon as you realize this is a pendulum, you should recall the range of motion, the equation of motion rather, is given by theta t equal to theta zero plus a certain sinusoidal function, right? Whether it's sine and cosine depends on the starting point. Cosine starting at the full swing, sine starting at the vertical point, t equal to zero, theta equal to zero. In any case, it's a sinusoidal function, and the angular frequency omega is given by square root of g over L. You better memorize all of that. You don't want to be deriving those on the spot, right? So that's the first thing. The second independent simplification we're taking is that we're taking a g value of 10 meters per second square, right? So that this 10 meter and the g cancels out numerically. We have a nice and round number of omega equal to 1 radian per second, which is a frequency of 1 over 2 pi per second, and give us a period of 2 pi second, right? How do we know that we should take that simplification of g equal to 10 rather than 9.8? Well, you probably don't until you look at these solutions and realize they're all nice and good fractions of pi if g were 9.8, and then we'll be dealing with decimals in here. So then, since we know that the range of motion was reduced by 1/4 in terms of theta, you might be tempted to say that, oh, it's time, the time should be, the total time period should reduce accordingly by the same proportion. So 1/4 of 2 pi, reduce 2 pi by a quarter, give you 3 pi over 2, right? And that's the wrong answer. It's the wrong answer because a pendulum motion is not uniform, right? It doesn't move back and forth with a constant velocity, constant speed. It's faster and spends less time in the center of the vertical line and spends more time in the full swing. So when you remove a quarter of the angle, you remove more than a quarter of the time, right? And that relationship is none other than this sinusoidal relationship. I put it in graphics here, right? I'm plotting theta versus this quantity here, omega t, which is the phase angle. Yeah. So we have phase angle in the x-axis and this real angle in the physical world, theta, in the y-axis, right? This theta is very small, close to zero, for a pendulum to work properly, and the phase angle goes from 0 in here, 2 pi in here, pi on the other side, and back to 2 pi to the original point. Right? So there are two completely different angles. Don't confuse yourself. So the question becomes, if at zero phase angle, the angle theta t is theta 0. At what angle does theta drop to half? And we know that cosine 60 degrees equal to half. So this the point we're missing here on the other side is symmetrical, right? So it takes 60 phase degrees to move from the full range to half the range, right? And 60 degrees is a third of this one-way swing, 180 degrees. One-way swing is 180 degrees. You remove 30 degrees, you drop the phase angle by a third. And so you drop the time period by a third. So you have 2/3 of the time left, which is 4 pi over 3. That's the correct solution. One other detail to point out, you might think that, oh, when this ball hit the wall, it's hitting it at an angle slightly different from 90 degrees. It has a little bit of upward motion, and when it bounces back, it should have also a little bit of upward motion. So this motion here during the collision is a little complex. That may be true in the real world, but not in the limit we're considering here, a very small angle theta. Angle is very small. Your incident angle is 90 degrees, and you don't need to consider that complication. So as a summary, this is a good problem that tests your knowledge and experience with regard to taking approximation, right? It's this whole thing is about a small angle approximation. That's when this equation of motion is valid. That's when the omega is equal to square root of g over L. Another approximation, not related to small angle at all, is to approximate g to be 10 rather than 9.8. What you cannot do is to say, oh, because it's small angle, everything is about the same. Therefore, if I reduce the range of motion in theta by a quarter, then I cut back the total time period also by a quarter. You can't say that because no matter how small the range of motion is, if you look at the change of theta versus the phase angle or versus time, it's always a sine wave.